Okay, so what we have here is a Platts binary system in which we have two objects going around in a circle because of the gravitational force that is attracting to each other has to put them in that path. And what we know here is that we know the tangential velocity of these two masses as it's going around in the circle, and that the masses are the same. What it's asking for is, given the total period that it takes to go around this whole circle and the tangential velocity, it's asking what is the mass of these two objects right here in order for it to stay in that motion. So what we're going to do is we'll just apply the inverse square law for these masses. So if this is mass m1 and this is mass m2, we can say that this force that is attracting each other is going to be equal to g m1 m2 over 2r squared. And it's 2r because this is the distance between this mass and the other mass together, which is really going to be equal, simplified, g m1 m2 over 4r squared. And since it's moving in a circle, we can then equate the force vector with mv squared over r. And since m is going to be equal to each other, it doesn't really matter. And v is the tangential velocity. So here's what we have now. What we want is we want this mass, and we know that these m's are really the same, so we can just put those together as gm squared over mv squared over r, so that's going to be fine. However, we arise with some kind of issue. We're looking for the mass, but we don't really know what the radius is, because once we end up solving for this, so like this is gm squared over 4r squared over mv squared over r, that's all fine and good, but then we end up with, okay, so gm squared, right? That's equal to 4mv squared r. Great, but how exactly are we going to be able to find r squared? Because we don't know r. We only know the period in this velocity. Well, since it's giving you the period, we could then apply Kepler's third law, which is t squared is equal to 4 pi squared over g me a cubed. And really, a cubed is actually the radial distance, which basically means that the radial distance from a circle or the semi-major axis. So really, we can name this is actually going to be, let me just erase that. This is going to be r. So the good thing is, now that we have these two equations, we can cancel out for an unknown and then solve for what we really want, which is m. So really, after you cancel this out, you say, okay, so gm, that's going to be equal to 4v squared r squared. And r squared, that's going to be equal to gm over 4v squared. So now we have this cubed, so we're going to say, okay, well, let's just plug this in to here, which is going to be equal to this quantity squared because it's going to be r cubed. So that's going to be t squared is going to be equal to 4 pi squared over gm times, we're going to say that this is going to be the square root of gm over 4v squared cubed. Or really gm over 4v squared to the 3/2. So now what we want is, we're like, oh, okay, well, this is some nasty algebra. We're going to have to end up canceling, things out, which is just as fine. It's just it's really much more of a pain in the butt than anything. But we can handle this because we're physics majors. Okay, that was some crazy algebra, but basically I just skipped to that to solve it for you and leave you without the whole messy stuff. So anyway, what ends up happening is that we have the equation m that's going to be equal to 4 to 3/2 times v squared times the period squared over 4 pi squared and the square root of g. And now that we have our actually converted constants to SI units, we can say that m, that's going to be equal to 4 to the 3/3 times 220,000 meters per second squared times 1,244 160 seconds over 4 pi squared square root of g. And if we calculate that, that's going to be approximately 1.4937 times 10 to the 21 kilograms. That's rather big. It's pretty big.